So the second lecture on planets that orbit other stars is going to focus, review a little bit on the discovery of extrasolar planets, but then also we're going to discuss the prospect of life on other worlds. So other planetary systems, we kind of already talked about this at length before, but just as a review, we can't really see a planet in the process of being formed. It takes a long time for these things to take place, millions of years. However, we do know from various nebula that there are protoplanetary disks out there orbiting young stars, and that this dusty material is most likely what planets form out of and what we think our solar system formed out of, similar protoplanetary disk. If we're able to block out the light from the star at the center, then we can see this disk pretty clearly, and these confirm some of the ideas behind the solar nebula and how our solar system actually formed, because we see a similar kind of disk to what we would expect. So once a planet is formed, how do we find it? I failed to mention last time that planets cannot generally be just taken a snapshot of. Why is that? Because they don't generally give off much of their own light. They're really just reflecting light from the star that they orbit. So the reason that we can see Jupiter, for example, is because of the sunlight reflected off of that. But you could imagine that if we were at a great distance from Jupiter, we would not be able to see it that clearly. It's only because we are relatively close to Jupiter that it's able for us to see it. So if the prospect of taking a direct picture of a planet is very daunting, how then can we actually find a planet's existence? Well, we talked about the wobble that takes place due to the gravitational tug of the planet on the star. And that can be detected through the Doppler shift in the star's spectrum. We see it red shifted when it's at one point in its orbit, blue shifted at the other point, and we see this periodically taking place in a predictable way, which leads us to believe then that there must be something orbiting it that's unseen. Another method we can use is the transit method that I discussed at length as part of my research that I've used, which is looking for the dimming of the star with when the planet passes between us and the star. There are some more exotic methods of detecting extrasolar planets. One such method is called the gravitational lensing effect, which uses the fact that light rays are bent to focus on a more distant star that wouldn't focus quite like that if the planet were not there. The disadvantage to this technique is that though it's able to find very small mass planets, you don't need much mass for this effect to take place. The bad part is that once we are out of that advantageous alignment, then it's gone. The effect is gone, and it can never be recovered. So there's no way to independently confirm these kinds of discoveries, especially because they generally tend to be pretty far away from the Earth. So unless there's another technique we can use, there's no way to confirm this planet's existence. So another interesting thing about exoplanets that I didn't really discuss at great length, I mentioned some things about hot Jupiters and whatnot, but it turns out that because the bigger planets are easier to discover, in other words, the bigger planets are going to create more of a Doppler shift because they're gravitationally pulling on the star more, or they're going to dim more of the star because they're larger. So either for the transit technique or the radial velocity technique using the Doppler shift, both of those are more sensitive to larger worlds. And because they are more sensitive to larger worlds, and these were the worlds that were discovered first. So most of the planets we know to date are these very large Jupiter-sized gas giant planets. We even know of some brown dwarfs, although not as many as we might expect. But we do know mostly about these larger planets. Most of the planets we know about are the larger worlds. That's not to say that smaller worlds don't exist. It's just that we have to be a lot more careful, and um, our techniques have to be very refined and precise for us to be able to be sensitive to some of those smaller worlds. So that is why, as of today, most of the worlds we know about, most of the planets, are these Jupiter-sized worlds. And a lot of them, in fact, are these hot Jupiters that are kind of shown here in the diagram, being that they orbit much, much closer to their parent stars than our Jupiter orbits in our solar system. So here's a sample of some extrasolar planets, and they're depicted at their distance from the star that they orbit. And you see our solar system is a little more than halfway down the list here. Jupiter is pretty far out there, around 5 AU. And you see that most of the other planets that are listed here are inside that distance to the star. And that there are very many that are even inside the Earth's distance to the star and that are much larger than the Earth. So these are where we get these ideas of the hot Jupiters. This list here is pretty small, actually. We've only been at this since the mid-90s. 1995, the year I graduated from high school, was the first year that was the year that the first planet was discovered. The first planet orbiting a sun-like star. There was a planet in 1991 that was discovered that was orbiting a neutron star. That's really like a stellar corpse, and we'll get to that when we talk about the life and death of stars. But the first one that was found orbiting a star like the sun was in 1995. And so we've only been at this for less than 20 years, but we've gone from that one single planet in 1995 to hundreds and hundreds of planets. And it's just tremendous how many are being discovered and how quickly they're being discovered. And still, we've only scratched the surface because we've only looked at planets that are relatively close to the sun. If you remember far back in, I think it was one of our first lectures, where I depicted the Milky Way and a small circle around our solar neighborhood where all the known planets to date exist within that circle. So there's this huge galaxy out there that contains countless planets that we just haven't been able to discover yet. So this sample is really just a tiny taste of what's out there. Now, I did say that that it's very difficult to get a direct image of a planet, and it's actually extremely difficult, in fact. But if it's the case that the planet is far enough away from the star, and the planet is large enough to give off a little bit of infrared heat and radiation, then when we look in the infrared, it's possible to maybe capture an image of the planet directly. And this is got to be a planet that's fairly close to us. So this is the first image of an exoplanet that was actually successful. There are precious few images like this, and new techniques are being employed to try and get more direct images of an extrasolar planet. For example, something that they're trying to do is block out the light of the star itself, and somehow within that, subtracting out the light of the star itself and the glare, sometimes you can maybe see the presence of the planet's light itself. But that's very, very difficult, and it's really just a pioneering technique at this point. So we don't have very many images. This is one of the very few that exist. So now that we know that other planets are out there, what about life on these other planets? That's the big question that sticks in most people's mind. Well, the only example we have of how life develops that we know of is the history of life on Earth. And so to think about how life might form on other planets, the best we can do is look at our lone single example of how life formed on the Earth. And so for much of the history of Earth's existence, life was basically just single-celled organisms. And only slowly did more complex life forms evolve and develop. Um, there's a Carl Sagan episode of Cosmos that lays out the history of the Earth and represents it as one calendar year. And so if you could take the entire history of the Earth and compress it to one calendar year, then for most of the year, you didn't have anything really going on. You may have had these one-celled organisms, but you didn't have complex life forms. And then later on into the year, for like about 3/4 into the year, so that would be what, I don't know, October or something, you would have more complex life forms that started to develop. And then in your calendar, the age of the dinosaurs didn't even take place until Christmas Eve, so towards the end of December. And then our whole history as humans on the planet Earth happened shortly before the ball drops on New Year's Eve of the next year. So the entire year has gone by and we're just this tiny little snippet in time, which is really humbling. So, we've talked about our place in the cosmos and how small of a place we occupy, but also if you think of in terms of time, how small of a time we occupy as a history for our species, it's also very humbling. We've only been here a relatively short period of time compared to the history of the Earth. And so, how does life form? Well, chemically speaking, it forms basically out of the ingredients, which are carbon and water, nitrogen and oxygen. These things have to combine into amino acids that then can form into DNA, and we can have more complex life forms from there. So, the Miller-Urey experiment verified that it's plausible, given the conditions in the early Earth, that these rich organic molecules could form spontaneously just from the conditions on Earth. So they took the gases that were thought to exist in the early Earth and they sparked them with sparks, which are supposed to simulate lightning, which was taking place in the primitive Earth. And then over time, you condense this and you see that you end up with like a tar-like substance, which consists of all these dark, rich organic molecules that formed basically out of the raw ingredients that were present in the early Earth. So this verifies that it's plausible that that life just sparked on its own out of the ingredients that were here on Earth to start with. Once you have cellular life, it's still a long road to complex organisms. First, you're dealing with no real internal structures and no DNA, and then later on, you can develop these more complicated things. But what's interesting is that the early atmosphere is much different from how it is today. It was very, very replete. In other words, it didn't have very much oxygen. And so it was only due to the presence of cyanobacteria where that changed into an oxygen-rich atmosphere. And we talked about that when we talked about how there are examples of organisms which profoundly change the atmosphere and climate of a planet. So, we talked about that in terms of climate change and what we're doing as humans. But cyanobacteria did it many, many, many billions of years ago. And so once that took place, then we had an oxygen-rich atmosphere, and other organisms arose that could thrive in that oxygen-rich atmosphere. And so greater and greater complexity evolved over time. And that's how we know, that's basically all we know about life on the Earth. And the history of life on the Earth. Actually, that isn't all we know about the life on the Earth. That's a silly thing to say. That's life on Earth is the only example. So that's the history in a nutshell of what happened on Earth. And so with that as our example, how can we move forth and figure out what might be out there on other planets? Well, we've searched some other planets in our own solar system. We've searched for life on Mars. As we talked about when we talked about Mars as a planet, we know that there is evidence that Mars was most likely warmer and wetter. In other words, it had running water at some point in its history. And so the probes that have been sent there have looked for the presence of some kind of microbes or other living organisms, but there wasn't any kind of conclusive results that were shown, but that doesn't necessarily rule out this idea. It's possible that maybe some life exists in some little niche there clinging to life on Mars. If so, it would be in, a microbial form. Fossils, maybe there's ancient Martian fossils that we saw when we had this asteroid hit the Earth in 1990. I don't remember, it was the mid-90s, but this particular asteroid seemed to exhibit what looked like possible fossil life, and the asteroid was thought to have come from Mars. So that could be evidence, but it's really difficult to say for sure. But even though we don't have conclusive results of any evidence for sure of life in our solar system other than Earth, that doesn't mean that there isn't life out there. In fact, if you think about it logically, it would be more surprising if there were no other life out there than if there was. So that doesn't mean, by the way, that the aliens have been here. There's a big difference between life existing elsewhere and it having the mobility or capability to possibly get through the vastness of space and to our planet, much less why another species might be interested in the Earth is completely unclear. So I do not want to take this as me condoning the idea that alien life has visited the Earth. I personally think that's very implausible, but I do think that the possibility of life on other planets is very, very plausible. And so how can we think about this logically? Well, one way to try and quantify it is the use of the Drake equation, what's called the Drake equation. And so this equation parameterizes all the different things that you need, the ingredients that you need for intelligent life to be somewhere else other than Earth. So if you want to figure out how many intelligent civilizations there are, we'll call that N sub I, number of intelligent civilizations. That should be roughly equal to the number of stars. First, you need the number of stars that are suitable for life. Then you need the fraction of those that actually have habitable planets. And then you need the fraction of those that have life forming on them. In other words, that not only is it habitable, but that it is inhabited. And then you need the probability that inhabitants, those life forms, have evolved to the point of intelligence and being able to contemplate their position in the cosmos like we can. So when you factor in all of these things, you come up with an equation. And this N sub star, the number of stars suitable for life, and F sub p, the fraction of stars with habitable planets, these are numbers that astronomers like me that study extrasolar planets are starting to get a realistic picture of, just starting to get an idea of realistically, what fraction of the stars out there are going to have planets that are habitable. We're starting to nail down a number there that is more reliable. But based on some reasonable estimates, then you can ascertain that there ought to be thousands possibly tens of thousands of intelligent civilizations just within our Milky Way galaxy. And recall that our Milky Way galaxy is one of just countless galaxies in the entire universe. So if there are thousands within our galaxy alone, just imagine the amount of life in our entire universe. The cosmos is literally probably and most likely teeming with life. It's just that we don't really have a way to know that for sure right now, other than this is granted kind of speculative, but it's reasonable numbers. It's a logical way to approach the problem. And so based on those ingredients that we need for life and approaching it from reasonable estimates, then it's fair to say that it's very likely that our universe is full of life and we're just one of many of those life forms in the universe.